Well, greetings and salutations, everybody. I had somebody decided, flat earther decided he was going to come over today and tell me that my modeling of Miles Davis photograph was completely wrong because, of all people, Ranty actually uh, apparently did some kind of magic and modeled it out. And of course, I was given a link and given a timestamp to a video. Y'all gonna love this. Now, in the Hangout, they came up with this little spreadsheet, and I'm not even going to go into the to this side of it. Okay, this is, and I understand what they're doing here, and I just don't have the time tonight to go into all of this. Okay, but I'm just going to give them the flat Earth part because this is going to be the easiest part. Flat geometry is the easiest. Okay, it really is. Um, Now, what Randy did, well, hold on. Where is it? Where Now, what Ranty did was he uh he puts on this presentation about what do you call it? About angular size. Alicia. He puts this presentation on about angular size, and he wants to use that as a way to test the heights of the objects in Miles Davis's thing, and which is cool, you know, if you do it right. But if you don't do it right, then what's the point? Now, in this little demonstration here, he starts talking about, something at a certain distance. Using a triangle is going to give you something's angular size at that distance, and that's true. And I have a favorite website that I use on this. As a matter of fact, I'll even show it to you because it's got all the different types of triangles that you can measure stuff out on. And I personally, it's literally one of my favorites. It's this guy right here, rechneronline.de. It's all in English though, so don't worry about all that. And you got all the different types of triangles: isosceles triangles, right triangle, regular triangle, where you put all the data in, etc. I love it. I use it all the time. Anyway, um, so so Ranty is getting clever, and he's pulling out the angular sizes of objects. Now, please note right here the Miles Davis photos. Now, he says he was at 210 meters. I would put him down actually a little bit lower, probably about 205, 204. But nevertheless, all the photos, and Ranty even accepts that and uses that number um, in his demonstration. So eye level would be at 210 meters per all the math that he did. Now, the problem is that there's nothing in the entire presentation from Miles Davis that's 210 meters, with the exception of the bridge and obviously his height. Everything else is larger. Okay, now remember that, which means that you have two triangles that you have to do, namely one below and one above. Okay, if you have a object that's larger than 210 meters, obviously you have a triangle above and a triangle below eye level. Simple? Okay. Now, it's also something that he showed here in the calculator that he used online, and it's also something that he showed here in his own diagram. Okay, there is distance above. Okay, and please note that this red line of a distant object, the bottom here, is not at this point. Okay, at the point of the bottom of the bridge. Okay, we all cool on that? Oh, and he also made one other point, which I thought was funny. He says the angular size of the bridge is well, he has it as 0.26738 degrees. Now the problem is that he was actually measuring for 45 kilometers instead of 46.5, which is the actual distance. So that was it's forgivable. The number is right for what he calculated, but unfortunately his distance was wrong. And I haven't checked up on this one, but their size is actually a lot different on this as well. But for care knock. But he says that the angular size an angular size greater than 0.26738 will make the other object appear higher than the bridge. An angular size lower than that will actually make it look lower than the bridge. Well, that's not exactly true, Ranty. At that distance, you are 100% right. At that distance. However, a further distant object can actually have a smaller angular height or angular size and still appear above the bridge on plane geometry. Okay, and I'm talking about across a plane here. No, no tricks, no wacky stuff on a plane geometry. Okay, it can still be above it and still have a smaller size. Now, what I did, I made this a while back, but and I wanted to use it like once or twice, but I never got around to it. But this is what I have here. Okay, this is calculating out the angular size, and please note that the hold on a second. The angular sizes they equal out to be the same as what I have written over here, and these are the angular sizes that we're worried about right here. And actually, just these are just dummies. They're just sitting at 100 by 100. But and what you have is you have at eye level, you have an angular size below and an angular size above. Okay. For example, the bridge is 259. Now, if I were to turn around and put this at the 4,500, 45,000, then I would get the 267 that he had. Okay. But that's the below. That's this angle down on the bottom. Not including this angle because obviously it's coming up to eye level. There's no calculation for above, so obviously it's there. Now let's see. 46,500. This is the actual distance. This is the actual height. But like I said, his calculation was right for the distance he put in. He just had the wrong distance. Now, everything else. Now, if I were to push this out, now I already did a little example over here under the same exact math. If I had something out at 100 kilometers and it's only 400 meters tall, and it's only got 0.229 angular size, it will still be above the bridge. It's smaller in size, and it'll be above the bridge. And the reason why that is because of the fact that not only do things come down from the top, they go up from the bottom on plane perspective. Okay, pretty simple. Okay, I mean it literally is. This is no talks of anything else. This is just perspective drawing. Things go up from the bottom and down from the top. Anything that is above your eye level will always be above your eye level, regardless of the distance. And anything that's below your eye level will also remain below your eye level. Now, now what Ranty did, like I said, these are the actual numbers above eye level, below eye level. Okay, you notice as distance increases, below the eye level goes lesser, but it doesn't go beyond 0 because parallel lines never cross. Or excuse me, not parallel lines, but the lines don't cross. Parallel lines is something else that would be for eye level and the plane. But these are the actual numbers. Now, what Ranty did, I'm sorry, I just find this hysterical. Now, what Ranty did, let me put it at a part where he's got it. Okay. Now, what he did was with the measurement that he had, and I'll even leave it at that. Screw it. 45000. Okay. At the 0.267, right? He pulled out a ruler and he set it to the height of the height of the middle post, right? And he set that limit to 0.267. Okay, makes perfect sense. Okay, that's a cool way to do that. Bravo. But what he did for the remainder of his angular size measurements, for all the rest of them, he left it at 0.267 here, okay, which would mean that everything's size starts down here, which is not the way this works. It's not the way it works at all. Okay, as a matter of fact, I mean it's asinine to do it that way. Now he had me going. I was like, okay, let's see what he's got to show. Now what he's showing after this is that the size of Michael Bin, uh, according to their measurements of angular size on the globe, which was basically they reduced the hidden height and the actual height. You know, it's basically actual height minus hidden height, and then put that at that distance. Which I understood what they did, but the problem is that you have to declare where the horizon is at that point, and all of your measurements are not going to start at the base of this. Okay, the horizon is actually a good little bit further, from 210 meters. I think it was like 51 kilometers away. Okay, so still got a good bit of distance beyond that to start doing your measurements from. But he left all of the measurements that he did. He left the ruler. He did all of his benchmarks here above it, but he left the ruler stuck at this spot at the bridge's height, and which basically eliminates everything about the distance. He just wanted angular size, but his angular size problem has to do with the fact that he's starting everything from down here, which would mean that basically this would kind of, I don't know, kind of, let's say if I was using the measuring point of this tower right here, all of his measurements are done from this point. So that means that it goes up, up, and then all the rest of them would be, you know, I guess you could say, like, let me get the size here real quick. I'm just going to have a little fun. The measurements that he's doing, group, shape outline, red, weight. Okay, the measurements that he's doing from that point are going like this. And then the next one further, if you had a smaller angular size, would be like this, all at this level. Okay, and he's wondering why why it doesn't work out. That's because he basically stopped everything's size at that point, forgetting the one very important thing that flat earthers love to yell about, and that is uh, things get smaller uniformly. Okay, so that's basically what he did. So long story short, his entire demonstration that he went on to do, where is it? There it is. The entire demonstration that he went on to do is all from that same point. All of them. All of his measurements that he did were from that point. So, Ranty, you need to get your math straight, bruh. Because what you should have done, let me show it to you like this. I'll just use a screen cap of your spot here. Watch this. Go for a full screen. Okay, so print screen. 1 second. I'll even do that right here. I don't know why I didn't set that up, but crop to here. And then duplicate that. Crop to, come on, there we go. Crop to here. Now, once you had your scale, okay, this being the degrees at distance, what you should have done was shown how much above and how much below the known reference point was. Okay, for example, where'd that go? For example, let's get one that's got some distance on it. Okay, Michael Ben. Okay, it should be 0.225 above. So that puts that. We gotta do this. Okay, so 0.225 above, and then below was 131, which is, I'll just put it about there. I'm not gonna be able to nail it out here because I got snap turned on and all that. Okay, now I understand, and I had also the same problem that Michael Ben, uh, given the measurements on Google Earth, um, I think I came up a little bit too short, but not this much short. I came up just a little bit too short. But I think you'll notice that this right here is a pretty big way to be off. Okay, so all in all, here's the numbers. You can work them out yourself. Okay, you have to have eye level separating a top triangle and a bottom triangle to get the distance of above and below the bridge. Now you'll notice that everything is above the bridge, with the exception, of course, of the bridge. Everything. And here's my height. Oh, and by the way, you can look at these. This is how I got these right here. So you can go ahead and look at those and incorporate it onto yours. And this was just the addition of the two. Okay, so everybody, just go ahead and do that, and you'll be able to do this all by yourself. And yeah, okay, but and that's how that works. Okay, so Ranty's thing was a complete and total farce. So okay, we all good? So thanks, Ranty, for not showing how to do math correctly. You guys have a great night.